stuff. Yeah. So, okay. So let's just make sure we're all on the same page here. Okay. So, right, what you guys have been working on is to go through the computer science ones, specifically this one, right? Coding with Minecraft. That's the one. Yeah, okay. That has, of course, 10 modules, right? And what y'all's project is basically the 10th of them. So what's the whole point of the various projects, right? And they're broken up into really small bite-sized chunks, you know, functions, iteration, array, some AI stuff, events, right? So I think we did one of them where we just like we made it so that when you typed a particular chat command, 100 chickens spawned above you, right, or whatever. Um, okay, so what you guys are going to do in this, right? What it asks you to do, and what I want you to do, is to synthesize. So you did a bunch of stuff in all of the different submodules, right? Learned how to do loops, learned how to do, you know, all of these basic things. And what I want you to do is kind of put it together and make, you know, something kind of creative. Okay. Now, the goal for this is basically um, make 4 things, okay, tools, whatever, right, that you could use like if you were in a survival game of Minecraft. All right, so now what kind of things could those things be? Well, so those of you who have played Minecraft before, what do you kind of need in the survival mode? Okay, you need like actual material tools, but in terms of the gameplay, what do you need to be able to do? Yeah, okay. So you could do stuff that would be like have the robot build you a little farm or and tend it to, for you, or build you a simple little hut that's, you know, something like that, right? Okay, so those kinds of things. And what I don't want you to do is just do exactly what's in the previous 9 lessons, right? I want you to kind of like synthesize here and do something clever and interesting and fun. Uh, yeah. Okay. Um, and I mean, you could do some amazing stuff in this. So I think I mentioned this to a few people. Well, actually, remember last week when I said I had watched a video on something and I saw this new way to think about two's complement that where we think of the last place as the minus 128th place. I don't know why that never dawned on me, but whatever. Um, that was actually in a Minecraft video that I was looking at where a guy built basically a fully functional 16-bit computer in Minecraft using just crap tons of redstone and pistons. And those of you who played the game know what those things are, right? Uh, like a fully functional computer. Right now, it was gigantic in terms of the game world size, and it probably took him forever to put together. But it was really, you know, kind of cool that you could do that sort of thing. So, Mr. Prusen, are we alive? Yeah. Well, I'll give you guys a hint. If you ever are over at Fidel, don't eat the chicken. So, anyway, Okay, yeah. So that's what I want you guys to do, right? Is synthesize, and the real goal here, and just um, to kind of pull back the curtain a little bit. So this is something that you know I was sort of beaten over the head with when I was a kid, right? You guys ever seen Bloom's taxonomy before? Okay, so this is sort of different types of learning and knowledge, right? What's the lowest form of learning? Yeah, just knowing things like facts and dates and basics like that, right? And then what's sort of above that in terms of thinking? Actually understanding what it is, being able to apply it, being able to analyze it, being able to synthesize stuff and put it together in new ways. And then at the tippy top is sort of evaluating, like, did this work? What do I need to do to kind of fix it, right? So the intent here is I'm trying to push you guys towards the top of the sort of learning pyramid, if you will, by taking the things that you've learned and kind of putting them together in interesting ways. Okay. Now, in terms of rubric, well, Cody, let me think of let's think about it together. So, uh, I'm asking you to make four cool things, and the project is graded out of 4 points because, huh? Yeah, basically one thing that doesn't suck. Okay. And in particular isn't identical to something from one of the previous lessons, right? Because that would kind of defeat the purpose of the whole synthesis part, right? So yeah, is it supposed to be onerous? No, right? But I'm also like, and this is why I didn't put like a more formal rubric there. I don't want to cramp y'all's style, right? And I want to leave it open to some creativity here. I mean, you can do some really cool stuff even just with the programming part of it. So like last year, Owen programmed freaking Duck Hunt in the thing where you'd get a bow and a certain amount of arrows, and ducks would start falling from like a little stage thing, and you'd have to shoot them, and it would keep track of your points, just like Duck Hunt on the Nintendo. I mean, it was pretty badass. Okay, I'll just to pardon my French, but um, yeah. So like you can do some pretty interesting things with this, right? And I'm kind of I wanted to leave it up to y'all to have some room for creativity. Now, on the subject, then, depending on how you go about designing stuff, right? You may need to turn in basically like the world file, which would be the layout of the actual world where all the blocks and stuff are. If you need to, there's a spot on Canvas to put it. If you don't, well, then no big deal, right? I'll just make a random world and then off we go. So that's going to depend on where you go in terms of your design, whether or not you need to give me a world file or not. Does that make sense? Yeah. Okay. But what I need you to turn in, and in fact, let's look at Canvas just so that we're all on the same page there, um, is, well, obviously the link to your code, which you share from the Minecraft website, right? Because it's all kind of web-based. Um, Oh, looks like a lot of assignments got turned in yesterday in my other class. That's nice. Let's see, where were we? Assignments. Okay, so here's the the two submission things, right? A world submission if you need to submit a world file. You don't have to, that depends on what you do. But then for the code submission, basically all it is, and actually let me change this to a text entry instead of just a URL. Okay, so you get a text entry box. So, well, first thing you got to give me is the link to where your code is, right? So that I can actually run it. And then also in the text entry box, if there's any instructions I need to know, like for example, when we made the chicken command that made it rain chickens, well, I didn't know that I needed to type chicken. If you like, you could have written it, and how would I have known that I needed to type chicken? I mean, yeah, I could look at the code, but if there's any instructions or description kind of things that I need to know in order to look at your stuff, then put that also in the text box. Okay. So are we clear? This isn't meant to be to like be destroying you guys, but yeah. What is, however, being meant to destroy you guys is the other project. And I'm kidding, Cody. It's not really meant to destroy you. Well, I don't know. There's still plenty of Star Trek and plenty of time left, right? Okay, so the machine code stuff that we've, started talking quite a bit before break. Um, right, so we've written some simple programs that do things like, um, well, there's one of them, right, where we figured out how do we tell if a number is positive or negative? What do you do? What bit do you look at? Yeah, the far left bit, the most significant bit. Well, how could you tell if a number is odd or even? Yeah, you look at the far right or least significant bit, kind of same idea. Okay, so what I've done is kind of broken this up into 4 tasks, um, which is when you kind of put them all together and go through them, you'll end up with a program that does multiplication. Okay. So the first task is figure out how do you tell if a number's odd or even. Okay. And then we talked about the rotate operation that you have, right? So let me just write a number up on the board and let's make sure that we're clear about the difference between a rotate and a shift. Okay, so I'm just going to take this random bit pattern. Okay, if I rotate this right by 1 position, what's going to happen? This one is going to come around. All these other 7 are going to shift left. And then what's going to happen to this 1? He's going to rotate around to that position. Okay, so that makes sense. Yeah. And if I rotated by 2 positions, then it'd be the same thing, right? Just more shifting. Yes. Yeah, rotate right. So the instruction set only has a rotate right command. Okay, which does beg the question, how do you rotate left if you wanted to? Okay, so this is kind of sneaky. Let's think about it. If I rotate right by 1 position, well, like I just did there, how could I rotate left by 1 position? Rotate right by 7, exactly, right? So does that make sense that rotating right by 7 is the exact same thing as rotating left by 1? And that's why we don't have a rotate left instruction, because we don't actually need it. We can build it out of another one that we've already got. Okay, so that's sneaky, but not all that sneaky. Yeah. Okay. So that's a rotate. Now a logical shift of this thing. So let me write down the exact same number. If I logically shift this right, then first off, those bits shift just like before. Okay, so nothing's different there. But then what goes here is a 0. Okay, so the logical shift, somebody who falls off the boat gets replaced with a 0, regardless of which direction you're rotating. Okay, there is no logical shift instruction in our architecture, but that's okay because we can build it. Okay, so let's think about how we could build a logical shift right by 1 position using a rotate right by 1 position. Okay, all right, so you guys see the distinction between logical and rotation? Yeah, okay. All right, well, if I rotate right by one position, what's the bit that I definitely want to be a 0? The thing that got carried around to the end. And all the other ones, I want to leave them as they were. Okay, so let me take this resulting bit pattern from the rotation, and let me just copy it down like that. Okay, I want to leave all of the 7 right bits alone, and I want to force the left bit to become a 0. Okay, any ideas how I could accomplish that? Okay, and keep in mind, what tools do we have at our disposal for this? We only have the other instructions in our instruction set, right? There's only 12 of them. And we know it's not a rotation because we've already used that. We know it's not a jump. We know it's not a halt. So what was the trick when we did odd and even, or plus or minus? How did I flip the bits when we were doing like negatives? I used XOR and a pattern of all ones, right? So I did the old Texas two-step. Cleverly selected logical or bit pattern and appropriately chosen Boolean operation. You like my accent, Cody?
Yeah.
You do?
It brought me back home. You know?
Okay. You from Texas, boy?
Hey, I wish I could be from Texas.
Oh, yeah.
I try to be like you.
Yeah, okay. Well, you might try a haircut first. So,
I'm from Texas. What are you talking
huh?
about?
No, that'd be like you're from Alabama.
No, I will say that when I went to Texas, I didn't get one compliment. And I told my coach who I was staying with that I didn't get a compliment. I was really upset. He's like, because it looks like you're from out here. So nobody thinks it's, any different. I'm like, I'll take that.
Yeah, fair enough. You know, when I see you come in on Friday with a 10-gallon hat, then we'll be in. Now, what'll be better, of course, is if you come in with a 10-gallon hat and in the top part there's like guacamole, and if all around the rim there's like chips, right? Then we'll have a good morning.
That could just have an A in the class?
Well, you still got some Star Trek to watch, bro. Okay, so what's the problem? That far left bit we want to force to be a 0, and we want all the others to stay the way that they are. Okay, so Texas two-step, cleverly selected bit pattern, and appropriately chosen Boolean operation. All right, so what do you think our bit pattern is going to be? Which bit do I care about or not care about? I want this one to get destroyed. So I'm going to put a 0 there. All the other ones I want to leave alone. So I'm going to put 1s in those positions. Okay, so that's my cleverly selected bit pattern. But now I need to think, what's the Boolean operation that I want to do? And when I say Boolean operation, what do I mean? I mean and, or, XOR, not, all of those things, right? Those are Boolean operations because they operate on things that are either on or off, true or false. Okay, so we've only got 3 to pick from in our instruction set, right? And, or, and XOR. Which one? And. Yeah. XOR is how we flipped bits. And is how we kill bits. Okay. And let's think about why that is. We want to force this bit to be a 0. Okay. And so by putting a 0 here, if I OR against a 0, am I guaranteed to get a 0 here? Or, not and. No, because if this bit's a 1, what's 1 or 0? 1. That's not what I want. Okay. Similarly with XOR, what's 1 XOR 0? 1. It's not what I want. Okay. But if I put a 0 here and I and, no matter what is in this position, am I guaranteed to get a 0 there? Yes. Okay. So that does it. Okay. Then for the other 7 bits, under what circumstance will I get a 0 there? Only if the original already had a 0. And under what circumstances do I get a 1? Only if the original already had a 1, aka they were both 1. So the other 7 bits are preserved exactly as they were to start with. But I've sort of deliberately destroyed that 8th bit. Okay, does that make sense? Kind of? Well, you have some coffee, it'll make sense then. Huh? Oh, I haven't had mine yet because I pulled onto the mall and the mall is already full because students are parking their freaking cars in the freaking mall or something. I don't know. So yeah, maybe that's what I should do is start like a campaign in The Bachelor, right? For no student parking on the mall because it means that professors show up to class not with coffee, which makes them less good. And yeah, so anyway, we could think critically about this, couldn't we? Okay, so does that kind of make sense that if you want to destroy a bit and force it to become a zero, then you put a zero in that position and use logical and, okay? For destroying bits, yes, okay? If you want to flip bits, which is what we did when we were doing the subtraction stuff, there we used XOR and a pattern of all ones, okay? Because that meant that we were guaranteed to flip and get the opposite of each bit, okay? So, so this is why, I mean, I'm not just trying to be cute when I say Texas two-step. It's really two things we need. We need to use the correct Boolean operation and a bit pattern to go with it, right? It's not one or the other. It's got to be both, okay? Okay, so that basically would get us a logical shift by right because we've made sure that that far left bit becomes a zero. Well, if we can do logical shift one by right, or right by one, could we kind of do the same sort of thing going left instead? Yeah, okay. Now, why do you need to be able to go left and right? Well, what was the, let me just pull up the Wikipedia page while we're at it, right? The ancient Egyptian multiplication, or sometimes it's called the Russian peasant method. Okay, so like let's take this example here where they're multiplying 13 and 238. Now the answer is what? I don't know. Can't do that arithmetic this early in the morning. It's not 1904, it's a little bigger than that. All right, so what I'm going to do is I've got my two numbers here, okay, 13 and 238. All right, and I'm going to progressively double one of them and progressively halve the other, okay? Now, in this example, you could have done this either way, because could you double one of them and have the other, and there's two ways to do that? Yeah, okay, which one's better to double in this case? That's kind of a debate, right? Which one would you rather double? 13, why? It's smaller, okay? Whereas the advantage of having the 238 instead of would be that 238 is big, and when you have it, it starts getting smaller, okay? Now, we can actually do this both ways, and I'll deliberately do it both ways, although I'm going to need a little bit more space. So let me rewrite it. So we'll put 13 here and 238 there. Okay, so Cody votes to double the 13 side, okay? All right, so I'm going to double 13 and halve 238. So what's half of 238? 150 plus 15 plus 4, so 169. Yeah? Okay, double 26 is 52. Half of 169, where we discard the remainder, is what? Did I screw up? What? Oh, so it's what? 119, okay. I was just so excited to write 169 that, yeah, yeah. Okay. All right, so what's half of 119? 59, right? Okay, but we're discarding the remainder, so 59, right? All right, double of 52, half of 59, discarding remainder. No, you always round down. 20, 29? Well, okay. 50 divided by 2 would be 25, or 29. Yeah, 59. Yeah, 29 point something. And so if we discard the remainder, then it's just 29. Okay. Okay, good. All right, continue. What's double 104? 208. Okay, that one was easy. What's half of 29 discarding the remainder? 14. Okay. Double 208, 416. Half of 14 discarding the remainder. In this case, there's no remainder. Okay. Double of 416, 832. These are kind of nice. Half of 7 discarding the remainder would be 3, right? And I'm starting to run out of space, but we're almost there. All right, double of 832 is 1664. Half of 3 discarding the remainder, of course, is 1. Okay, and I stop when I hit 1. Okay, now on the side that I doubled, okay, which in this case I've written on the left, I want to cross out any of the lines where I have an even number in the halved side. Okay, so I look on the halved side, and which lines have even numbers? Well, the original one did. Okay, so I'll cross him out. I'll cross this one out, and those were the only two. Okay, and then I'm going to add the corresponding dudes from over here. All right. So what's, Cody, since you've got a calculator handy, what's 26 plus 52 plus 104 plus 416 plus 832 plus 1664? 3094. Okay. And what is the correct answer? 3094. Okay. All right. Now, we could have done it the other way, which was to double the 238 and have the 13. Okay. So let me put the 238 here and the 13 there. All right. So if I double 238, well, in this case, we don't have to think about it. We can just copy down the numbers from Wikipedia, right? All right. And then 13, we'd have 6, 3, and 1. Okay. So on the halved side, we cross out any guy that was even. In this case, it was just that one. And we add up the 3 remaining pieces, okay, or whatever's remaining on the left-hand column. All right, and so what do we get if we add 238, 952, and 1904? Well, what should we get? We should get the same answer, and of course we do. Cody's verifying it. Yep, 3094, okay? So that's the Russian peasant method, is this. Now, let's think about structurally what we've had here, right? Do we understand how to double and halve numbers? Okay. In arithmetic land, yeah, of course. And when we have something, what do we do with the remainder? Yeah, you just drop it off. Okay, there is no remainder. Okay, so division by 2, where you discard the remainder, is a logical shift right. Yeah? Okay, and this is, as I was telling my other class yesterday morning, in the sign of a good comedy routine, right, one of the things that great comedians do is they always go back to a previous part of their routine later on in the routine, right? Well, so I'm going to do that, but going back like a couple weeks. You guys remember when I told you about when I worked at Kohl's? and the lady came up with stuff that was 10% or 90% off, and she wanted to know what the prices were, right? And so how was I able to do that so quickly? Because 90% off is 10% of, and so what was I just doing? I was either, depending on how you want to think about it, moving decimal point or shifting digits, right? But division by 10 is the same as shifting digits one position to the right, or equivalently, the decimal point one position to the left, okay? Now, there is no decimal point here because we're doing integer arithmetic instead, all right? So division by 10 or multiplication by 10 is the same as shifting digits by one position. So in binary, division or multiplication by 2 is accomplished by shifting, logical shifting by one position, all right? And so if we can logically shift left and right by one position, we know how to handle the doubling and the halving that we would do at each step here, okay? Now the other thing, we crossed out and did not add the 476, for example, because the number on the in the other column, the 6, was even. How do we know how to tell if a number is odd or even? We do, right? It's almost as if your professor kind of built a hierarchy of assignments or little tasks that builds you up to a bigger whole. Yeah? Wow. The professors actually think about what they're teaching. I know, it's amazing, isn't it? Okay. Yeah. So yeah, this is how you could do it. Now, the one, I guess, difference between what I'm going to ask you guys to do in the machine code is with the machine code, you get to assume that both numbers are 12 or under. Okay, so in hex, it would be 0B or under. And the reason for that is, what's the biggest number that you can store in a memory cell on our computer as a signed integer? Signed, not unsigned. 127, right? Well, what's 12 times 12? 144. Okay, so if we have both numbers that are less than 12, so what the biggest we would have would be 11 times 11, which is 121, which fits just barely underneath the 127. Okay, so I've introduced that artificial limitation here simply for the sake of not having to worry about overflows or weird stuff like that. And that's only because our machine is an 8-bit arithmetic system. Okay. All right. Now, is this the best way to do multiplication? Well, it's certainly a way to do multiplication, but what's another way that a computer would be really good at? Right? How could I have done 13 by 238 if I wanted to be really lazy? Could I have just added 238 to itself 13 times? Okay, and used a loop to do that? Now, is that particularly efficient? Probably not. Particularly if I did it the other way, because if I wanted to do, I could have also done add 13 to itself 238 times. Well, clearly one of those is more efficient than the other, even though they give you exactly the same answer, right? So mathematically they're identical, but from a computing standpoint, which one would you rather do? You'd rather add 238 13 times than the other way, okay? So so task 3 on that was actually to just do it with repeated addition, right? And in doing so, you have to write a loop. Okay. Now, in this case, because like I said, the numbers will be 11, which is 0B, or lower, the loops won't go on for forever, right? Because at most, you'd be adding something to itself 11 times, okay? But there's going to be one problem, because what happens if one of the numbers is 0 and you do a loop? What happens if I asked you to do 10 times 0? And you said, okay, I'm going to add 10 to itself 0 times. It's just 0, but you got to program it right to make sure that it doesn't go into an endless loop. Okay. So for the purposes of that part, just assume that you have neither number is 0. Okay. just to simplify it slightly. Okay, and then this is the fun part, which is then after you get everything working, then go back and fix the zero part of it. Okay. All right. So how are you going to submit code for this? So like, how is your project going to look? Well, let me open up one of the examples that we had been working on. That's from my other class, so don't worry about that. Okay, you're basically going to give me something that looks like this for each of the tasks. Okay, so right, and obviously I didn't write all of this at once. What did I do first? I did this part, right, to make sure that I was thinking through the logic correctly. And then I put in the memory addresses and the actual translating it to an opcode so that I could make it a big long string and plop that onto the website, the little simulator thing, right? So right here where I've got this string, what I want you guys to do is to paste in the URL to the website that has your code loaded in. So all I have to do is copy and paste, hit enter, hit refresh, and bam, your code is loaded and I can run it and make sure that it works. Okay, and you're going to need that anyway to make sure that your code works, right? Because what's the point of submitting code that's broken? Well, that's true. Okay, but point being, you're going to need to you want to see if it's working at all, right? And because if it isn't, then you want to figure out why. Okay. Now, unfortunately, and this is on my bucket list to do, there's no automated way to go from this stuff, the assembly code, to the link to the website where it all just magically is ready to go. It's on my bucket list to write that software, okay? So that all you would have to do is type in the code, hit a button, and it would, process it and tell you if there were any errors, or if there weren't, spit it out and let you run it. Somebody find me 12 more hours every day and I'll have it done in a week, but, well, and maybe a very large supply of amphetamines that might help also, but, uh-huh, okay. Yeah, that would, but not every day. That's only 1 hour every day. Yes, but I'm also not very productive if I'm sitting at home with a migraine. Uh, kids these days. No, I really did have a migraine yesterday. I promise. I mean, come on. How much partying do you think I'm doing at Sunday night in Crawfordsville?
Who says you had to be in Crawfordsville party?
Well, that's true.
Indy's only like 50 minutes away.
That's true, but no, I just, yeah. All right, so are we clear here? Now, where are my prospective CS majors and minors? You guys better be able to do all four of them. Okay, you can do it. All right. All right. Please don't procrastinate on this because, as Owen can attest, nothing makes me more of a bitchy professor than when students are showing up the day something is due, being like, "So, how does hexadecimal work again?" And I'm like, "Yeah." So, okay. All right. Let's do something completely different. Um, which is I want to kind of go back and I want to go back and kind of to the very beginning of the semester. Okay, what was it we did at the very beginning of the semester? Yeah, we did a little bit of the history of computing. Okay, What else did we do? We took apart the computers and put them back together, right? Saw what all the parts were. Okay, and then after that, what did we do? Yeah, we got really small and we started doing logic gates and transistor level stuff. Okay. Um, and so I kind of want to go back to that and talk about how a processor is actually constructed. Okay. And what are sort of the parts of a processor, like if we start to kind of zoom in, if you will. All right, because ultimately everything is a bunch of logic gates, okay? But we've got sort of two questions. How are those logic gates, all right, so it's Java, let's assume, where is it? Um, how do you do it? Or maybe I just double click on it. What? Okay, why is that not, let's see. Hold on one second. I don't think that I have, oh, that's right, Java-jar, okay, there we go. Okay, oh crap, okay. I don't have the most recent version of Java. So, all right, I'll fix that. But let me go back and I'll just do some stuff on the board here. Um, so when we talked about transistors, right, we were using a particular kind of transistor called a BJT, bijunction transistor, or something like that. What was the symbol for it? It was that kind of thing, right? And what were the parts of this? We had a base, we had a collector, and we had an emitter. Okay. And this thing is a current controlled switch, meaning if we apply a current to the base, there's a very small amount of electricity that goes from the base to the emitter. Like it's actually energy is flowing. Okay. If we do that, it allows a larger current to go from the collector to the emitter. Okay. All right. And that we were able to use as sort of like a little switch, right? On or off kind of thing. But that's not the only kind of transistor that exists. Um, it's one of the earliest kinds of transistors, and in many respects, they're the simplest ones to work with. Okay. Um, but there was a second kind of transistor that we talked about that was also a BJT, and it was this guy. All right, so what's the difference between these two? What were they called? This is a what? This one's an NPN, and this one's a PNP. All right, what's the difference in function between them? They both work like a current controlled switch, but what's the difference? Okay, a NPN, what is an NPN doing if the base is off? The switch is off. What about a PNP? It's the opposite. Okay, so applying a current to the base of a PNP turns off the current from the collector to the emitter. Whereas applying a current to the base of an NPN turns the current on between the collector and emitter. So we might say that this is default off and this one's default on. Okay, so they're sort of backwardsy. Okay, does that make sense? Yeah? Okay, so there's a totally different kind of transistor that's manufactured differently. Okay, and it's called a MOSFET. Okay, which stands for metal oxide semiconductor field effect transistor. All right, so let me write all that out. Metal oxide semiconductor field effect transistor. Okay, and these things work in some ways similar to the BJTs that we used before, but in some ways different. Um, Two differences. They're constructed differently, right? And instead of being current controlled, they're voltage controlled. So I apply a voltage to the base, but no current actually flows. Okay. And through the magic of quantum physics, which I don't even begin to understand, stuff works. Okay. Now these guys have slightly different diagrams, and let's see if I can do it and not make it suck. Okay. So this is an NMOS. Okay, and then to go with it, there's also a PMOS. Okay, now the three parts have different names than the base collector and the emitter. We have the source, the gate, and the drain. Okay, they kind of work like collector and emitter, and we'll talk about this more, I guess, on a little bit more on Friday. Okay, and the difference between them in terms of their diagram is notice that the PNP, or this one's a PMOS, has this little loop, okay, which we've seen before, right? Putting a little loop there to identify that something's a little different, okay? Um, and so those two things are like how you would actually fabricate, well, today anyway, a microprocessor. It's going to be crap tons of these things, okay? And what we'll do is you could build everything with just NMOSes. You could build everything with just PMOSes. But what's really clever is when you put them together in kind of an interesting complementary way, okay, using both NMOSes and PMOSes, like I said, together in the right way, you get what's called a CMOS, complementary metal oxide semiconductors. Okay, the complementary refers to the fact that in some sense these guys are complements to each other. And so what we'll see is every time we have one of these, we'll also have one of those. Okay, and we'll put them together in interesting logical ways. Now, the end result will be logically the same as when we built the XOR gate with the 5 individual BJT transistors, right? So the net effect is going to be similar from, sort of y'all's perspective, but from a fabrication and power consumption and a whole other lot of reasons, these are superior. And these are superior in terms of making an actual chip, okay? Because so the BJTs, the transistors that you guys used on the breadboards, were pretty big looking things, right? Shrink that down to so that you could fit billions of them on your fingernail. Doesn't work quite down there now. Doesn't work. This does though. Okay, and so basically almost every 99 point whatever percent of integrated circuits that have been produced since the 80s have used the CMOS technique. Okay. So yeah, so we're going to kind of, look a little bit then as to a different way that we could build and or gates, those sorts of things. And then once we figured out a different way to build and gates, or gates, all of those guys, how could we put and or gates and all of these things together to actually start to build the pieces of a computer, right? How would I use and gates, or gates, etc., to build a circuit that does addition? Sounds hard, but it's not actually as hard as you might think. Okay, so that's I guess where we'll start on Friday. So, all right. I completely spaced on bringing the exams with me because I'm a horrible professor. So swing by and grab them from last week. and we'll do our retakes eventually. Yeah. The last one, yeah, the last hurrah. And in fact, I'll even give you guys an option, right? Would you rather retake it on Friday or Monday?
Please Monday.
Please Monday?
Please.
All right.
Another exam, a paper that is due, and I'm cutting late.
Uh,
It would be amazing.
I'll let you do it either on Friday or Monday, whatever your pleasure is. Okay.
I was going to ask, to be honest.
Okay. Yeah. Well, I'm the real MVP. So, all right. See you guys later.